Log on, tune in, find out. Another good idea from Cambridge.
Have a talk here, and the second I want to say that unfortunately some of the slides I prepared on some different system, and some of them are distorted, so I have to write something on the blackboard. It's a pity, but we have what we have. So okay, but first one is not distorted, so we can read it. So the goal of my talk today, I believe, is the following: the geometry plays the most important role in inverse problems. In fact, what I want to say is that the inverse problem in general is a kind of inverse problem of geometry, mostly. And the first statement, maybe it's not completely correct because it's not a mathematical statement. The second thing I want to say is that when you try to solve geometrical problem in inverse problems, you have to use some instruments which is suitable for that. So some instrument which also contains some geometric things inside. Such instruments I want to say are so-called Gaussian beams. There are in fact two types of Gaussian beams. I will say about this somewhat later. And the third idea which I want to discuss today is the following: that till now, most of the inverse problem related to Riemannian geometry. But what would be for more if our geometry is not Riemannian? For example, if it is Finsler geometry or maybe even more complicated things, what will be? So this is what I want to say. So let's start with the first thing. I start with problem which is solved many years ago, more than 10 years, and it's the problem of reconstruction elliptic self-adjoint operator, second order differential operator on the manifold, on a smooth, compact, if it's necessary, maybe not compact, it depends on the problems. If we can use different type of data for that. One of them is eigenvalues of the operator for compact case, and normal derivatives, for example, of the eigenfunction for Dirichlet problem, or traces on the boundary of eigenfunctions in the case of Neyman, or maybe more complicated differential boundary conditions. And we want to reconstruct the manifold and the operator. Oops, excuse me. First of all, by means of gauge transformation group, which is related to the operator, we can reduce our problem to the problem of reconstruction of a Schrödinger operator, corresponding to Beltras-Laplamy operator delta G plus Q on the Riemann manifold. So the first step is to reduce reconstruction of some physical parameters of second order differential operator to the reconstruction of Schrödinger operator. If we look at this Beltrami-Laplace operator, what we have to reconstruct, in fact, it is we need to reconstruct manifold, and we reconstruct matrix, and we need to reconstruct potential. Reconstruction of potential is somewhat specific problem. It is solved after reconstruction of metric. I want to stress on the first part. We have to reconstruct manifold, Riemannian manifold, and that's all. So this is in fact geometrical problem. Unfortunately, we don't have data which is suitable for geometry. We have a physical data, such as Dirichlet-Neumann map or spectral data. It doesn't matter. How we can do that? You see that this is distorted, so I try to rewrite it here. So the idea is, we use the boundary control method, so-called. The idea is to use physical processes related to hyperbolic differential operator. So we, instead of considering the, instead of considering the Beltrami-Laplace operator, we consider the wave operator corresponding to this Beltrami-Laplace operator, and consider the initial boundary value problem. Our data is the trace on the boundary, the solution, and normal derivatives of the solution. Sometimes it is said that it is Dirichlet-Neumann map, but in fact, we need to know for all solutions, we have to know the traces, both of them. How we say Dirichlet-Neumann map or Neumann to Dirichlet map, or it doesn't matter in fact. We need both data. Okay. The main idea of boundary control method is the following: is the so-called Blagoveshchinsky formula. This is the main analytical fact related to this boundary control method. The idea is the following: that if we know the boundary data or Dirichlet-Neumann map or Neumann to Dirichlet map or spectral data, we can reconstruct, we can just compute the inner product of these two functions. This is two different, maybe even more complicated. I might put here not F, but G. If we have two different sources, F and G of controls, we can reconstruct just by integrating. That's a small simple formula. We can find this inner product of wave. This is the main idea of the method. And now the problem is how to use this inner product to reconstruct, to solve the inverse problem. And this method is mostly geometrical one. How we can do that? First one, because of Holmgren-John uniqueness theorem, and by means of orthogonalization procedure, we can in fact reconstruct by means of this data. We can reconstruct not only this one, but this one. So we can add additional orthoprojector. And this orthoprojector on the field domain. What is the field domain? What is this orthoprojector? So we're just cutting function on the some domain. What is this subdomain? This is a set of points on the manifold which has distance less than t to this part of the boundary for this gamma. And this is the two analytical fact which is enough in fact for reconstruction procedure. How it is possible to do? And here we can use the Gaussian beams. It is the first time the Gaussian beam appears. This is asymptotic solution of this hyperbolic problem, which has the following properties. This is the ray-type solution. This is the formula. Unfortunately, it's also distorted, but not completely. It's possible to understand it. With complex phase and amplitudes. And this phase, which is the most important, because just phase determines where is concentrated this solution, satisfies the following properties. This is equal to 0 for any t in some point, only in one point. For fixed t, this is equal to 0 for x equal x from t. And more than 0 for any other point, everywhere. In this case, what we can see is that this solution exponentially small outside small vicinity, small neighborhood of this particular point. If we decompose our phase in the Taylor series, we can find this following decomposition. following decomposition. And it is possible to prove that this is a function, h from t is a matrix function, in fact. And this matrix satisfies the following important properties, remarkable properties, that imaginary part of this h more than 0 for any t. If we fix some t and made this function as imaginary part is positive, then it will be positive for any t. Such remarkable solution. Then the next properties of this Gaussian beams. What is this function xt? What is the trajectory of the centrum of this quasi-photon, the maximum amplitude of this quasi-photon? This is in fact point which moves along the geodesic of the matrix corresponding to operator. So this is absolutely geometrical things. It propagates along the geodesics, and velocity of this point is equal to 1. So in fact, if we have two positions of quasi-photon for time t1 and t2, and t1 and t2 not differ much, then the distance between 2 points is just difference of time, nothing more. So very simple things. And due to these properties, the quasi-photon for any time t concentrated close to a point, 1 point. And also it's possible to prove that this quasi-photon has no singularities at all. So this solution has no singularities, no caustics. Okay. Now how it's possible to use this solution? Assume that we take the sources f and f such that this corresponding solution will be quasi-photon. It's possible to do. Just explicit formula. Then what we can compute? We can compute this inner product, this one. I wrote this some picture here. So this quasi-photon start in the point z on the boundary somewhere and propagate along the normal geodesic just now. So in fact this quasi-photon for any time t concentrated close to this point, which is lie on the normal geodesic, starting in the point z, and the time t it is just distance from this centrum of quasi-photon to the boundary. Okay, now let's see what we obtain if we change parameters gamma, shrinks then gamma to some point. What we obtain? If and epsilon tending to 0 for the quasi-photon. If epsilon tending to 0, the centrum of quasi-photon shrinks to a point, just on this point on the manifold. And if we change parameter s, for example, increase it, then for some times the quasi-photon will be inside this domain m gamma s. In this case, projector, because UF is concentrated, it is just the same. We can remove this projector. It will be some constant, in fact, or some function which is smaller varied along with parameter s and t. So we have something which is. So if s is large enough, we see some practically constant. Okay. If s decreasing, then for some position, when, if somewhere here, it comes through the quasi-photon, and then our quasi-photon will be outside the domain m gamma s. In this case, projector of this function will be practically 0. It's O epsilon power m in any power m. So we can easily see, just changing parameter s, that quasi-photon is inside this m gamma s or outside. But what is it means if gamma shrinks to point y? It means that we found the distance to the point y. The distance from the point gamma at the t on the geodesic of this point till to the point y. So what we found the distance from one point inside this manifold to the boundary point. And if we change this parameter z, y, t, then we can find the distance from any point inside manifold to the boundary, to any boundary points. And this is so-called the boundary distance function. It is a geometrical object. It's the distance from the function on the boundary, which gives you the distance from particular point to any point on the boundary. And we can compute this just by means of using this formula, nothing more. Remark that we use one more geometrical object. This is a field domain. This is a number of points with distance to boundary section of boundary less than t. It's also a geometrical object. Now the boundary distance function is also a geometrical object. And after that, after we found the boundary distance function, all other things, it is more or less geometrical things. Using this boundary distance function as a point on some manifold. We can reconstruct a geometric copy of this manifold. It is a rather complicated process, but it's pure geometrical one. There is practically no physics at all. It's inside a geometrical process. So we see that in this particular problem, the geometry is the main thing. We have to reconstruct the manifold, Riemannian manifold. We use the main geometrical stuff, the geodesics, the boundary distance functions, the field domain, and so forth. Okay. So for theoretical problems, this type of Gaussian beam as quasi-photon is very useful because it itself closely related to geometry. Now,
a question?
Please.
So the Gaussian beams help you to go through conjugate points, but if I look here at the distance function that you use, you can hit a cut locus point. And how do you?
Gaussian beam, nothing happened with Gaussian, with quasi-photon.
I know, but if I do the geometric construction of the distance function, then I can hit a cut locus point. That point would go beyond the cut locus of this boundary point. And how do you then define the distance function itself?
There is nothing with cut locus. This quasi-photon center may be in this domain, maybe not. We just as switch. By means of this function, we can just switch. We can see when this switch taken place. From zero to constant. So this is an application. It will be something like this. It will 0, 0, 0, then jump, and after that some constant. We see that this is exactly distance to the point. There is nothing to cut locus. Not on this place cut locus appeared. Okay. But this is theoretical one. How about applied problems? Let's see. This is a so-called Marmouzy model, which is well known in geophysics. This Marmouzy model gives you some section of the S crust, and there are somewhere oil deposit. And we try to find out where is this oil deposit. What is the geometry here? We don't see the geometry just now, but let's see. Maybe I show the picture. This is the picture of rays, which is started from the boundary point. It is upper this one. This is the S surface. We start. This is some source, and this is the set of geodesics or rays inside the S, which is produced by means of this source. You see that the picture is extremely complicated one. There are a lot of caustics. We don't know where is there, but for example, we can say that there should be some caustics. And And many other things here, for example, also they are acoustic, and so on and so forth. And it's necessary to solve this. The problem is to find out the internal boundaries, interfaces inside S. They assumed, I don't know how, maybe those who deal with these things, geophysicists know better. They assume that they know the velocity profile. This is the velocity profile. The yellow and red, it's the velocity larger, and this is smaller. They know the velocity profile, but they don't know where is the internal boundaries. And it's necessary to compute these internal boundaries. But they standardly use the ray method. But there are so many caustics that it is difficult to use it. That is so-called the migration problem. So it's also inverse problem, reconstruction of internal boundaries by means of seismograms on the boundary. So they have set of sources somewhere. They change it and measured seismogram along this profile for different sources. We have a huge amount of data, and we have to reconstruct the internal boundary. But where they are? This is what we compute by means of different type of Gaussian beams, the so-called quasi-jets. They not as concentrated close to a point, but this quasi-jet solution concentrated close to a geodesic itself. It's maybe to write a picture. So this is, let it be geodesic. Then this is type of Gaussian beam, something concentrated close to part of the geodesic, and then moves this time. So this is as a jet. And what is remarkable in this, for this type of solution, Gaussian beams? The remarkable is the following. That first of all, they concentrated close to a geodesic, the same way, it's geometric object. The second one, that they don't have singularities also. These things has no singularities. The third one, that any high frequency wave field can be decomposed in the integral over this type of solution. So we start from some point as initial point, as a source. Okay. As a source. And somewhere here. And then take set of geodesics starting with this point. Along each of these geodesics, we compute this quasi-jet solution and then integrate. And we obtain solution everywhere. Remarkable thing that there is no caustics at all. The problem of caustics does not exist for this type of solution due to complex, because this solution is complex. And this is what we compute by means of this type of Gaussian beam, the quasi-jet solution. What is maybe next picture? This is the picture which obtained by means of this, the ray type computation. This is by means of pure numerical, but very, very, how to say, time-consuming procedure. And this is which computed by means of Gaussian beam solution. It is even better quality than the high time-consuming procedure, and of course much better quality than the standard ray procedure. And I believe that it may be useful in numerics and in application. Okay. So what we can see here, that in applied problems which solved just now in a not how to say good way, but still they try to solve it, and the main problem are also singularities of the ray field, singularities of ray field, also geometric character, the caustics. So also the geometry appeared in this problem inevitably, and is the most difficult problem. So I believe that I show that geometry is necessary to use as an applied problem, as a theoretical problem, because it is in the essence of this problem. To my mind, it is a good idea not just take in mind that there is some geometry and forget about this. It's necessary to use geometric language when we try to solve inverse problem. Geometric language. And in fact, those who deal with the inverse problem, especially in application, know this language. For example, the simplest things, simplest things, that how to measure the distances between 2 points inside S. The measure of distances should be closely related to measure to the corresponding geodesic distances, which geodesic corresponding to this particular problem. This particular problem related to conformal Euclidean space, this one. This is a metric tensor. And so this geodesic distance for this particular matrix is just time. So even on this step, geometry appeared. An elementary step that it is necessary to measure distances in time. Then they use the name ray or external Fermat function, but what is it? It's geodesic for this conformal Euclidean matrix. They use this is the physical notation. This is a geometrical one. Условный surface. It is a figuratrix corresponding maybe Finsler matrix. For the tropic metric conformal Euclidean space. For anisotropic media, elastic media, this function h satisfies this homogeneity property and nothing more. If we deal with atropic media, this conformal Euclidean space, the same things. If we deal with the atropic surface, this is the Riemannian manifold. And what will be with anisotropic media? If anisotropy is small, so such a slowness surface is convex still, then corresponding manifold will be Finsler manifold. And it's also a geometrical object. And we have to use it, because it is the essence of our problem. What will be as if we have a general anisotropy when slowness surface is not convex? Nobody knows. Geometries till now don't have adequate instrument. I believe that it's a good idea for geometries to try to put something in this question mark. It's very interesting.
Do you mean external anisotropic elastic solid?
Doesn't matter. Anisotropic. The anisotropy here is related to this particular function, h. It's Hamiltonian physics. Yes. And if this Hamiltonian is just homogeneous function, positive homogeneous function, as it is written here, then it may be general anisotropy. For example, for anisotropic elasticity, it will be just the case. This function is not convex, and corresponding geometry doesn't exist. Geometry don't investigate this type of problem. It's very interesting for me, but it is fact. Okay. So now we look once more on the quasi-photon and quasi-jet solutions. And this is the same form I have written earlier. This is a quasi-photon. Quasi-photon in elastic media, for example. This is a main term of asymptotic expansion written here. As I said, that the function x from t is the trajectory of geodesic, is the geodesics, and canonical form of geodesic, because time t is a canonical distance. P is the velocity covector here. So this is a velocity covector, is a unit velocity covector, in fact, here, for this particular geodesic. So this quantity has the geometric sense, but how about this one? This is quadratic form. Unfortunately, this things has no geometric interpretation directly, because it is not tensor in this field, but by means of simple transformation, this one, which contains this is our quadratic form, and if we subtract, this is a connection coefficient for this particular matrix, Riemannian matrix. This is a covector, velocity covector. If we make this transformation, we obtain the matrix, but it is not matrix. It will be tensor. It will be tensor. In this case, it will be geometrical object. And instead of Riccati equation for H function, we obtain covariant Riccati equation for modified tensor J. It's it's necessary to make some additional modifications. This is written. So simple modification of the quadratic form yield us the following things. First of all, it will be geometric object. This is a complex two covariant tensor in this case. And what is there in this equation? We have a section of curvature tensor. So also geometric object. Everything here is of geometric character. So, and if we see, this is one additional remarkable fact. If we look, this is a real valued function, this part. So the imaginary part of both G and H are the same. So imaginary part H is a tensor, and imaginary part H determines that this is a concentration close to a point. This the property of concentration of Gaussian beams. It determines the form of the quasi-photon or quasi-jet solution and so on. So the most important properties of this quasi-photon solution are of geometric character. Next things. What will be in Finsler geometry? In Finsler geometry, in fact, this is for quasi-photon, does not change too much. Practically the same. We obtain the same type of equation. Only we have to replace in Finsler geometry there is not covariant derivative. There is so-called delta derivative, somewhat different things. This is a really covariant equation for Finsler geometry. And instead of Riemannian curvature tensor, they appeared more complicated things. This is so-called the third Cartan curvature tensor of Finsler geometry. So another thing that if you try to construct quasi-photon in Finsler geometry, there we obtain also the main term of this quasi-photon has geometric sense. Everything is geometric sense. If you look at the quasi-jet, it's somewhat more complicated. For example, how usually construct the solution for quasi-jet solution in some media? This is a form of quasi-jet solution written here. So there is also quadratic form, complex valued quadratic form, which is imaginary part is positive. But there is some variables. It is a normal section. That we take the normal section to the geodesics and take Cartesian coordinate, just Q alpha, some Cartesian coordinate. Then this is the decomposition. It is concentrated close to geodesic because for large Q, this quadratic form will be imaginary part will be positive. And this is due to this small parameter epsilon, it will be exponentially decreasing function. But if you try to construct this on the manifold, there is difficulties. What does it mean, the normal plane? There are no normal plane on the manifold. What should be replaced of this normal plane? The normal plane here replaced on the surface which constructed from the geodesic. We start on the point on the geodesic, and in any normal direction, there is also important thing that in generally, in Finsler geometry, there are no, how to say, it's impossible to say that these two vectors are orthogonal. Because the metric tensor depend on the directions. But it is possible to say that this particular vector orthogonal to the tangential vector. And after that we put geodesics in any this direction and obtain some surface. And we take the distance as these coordinates. But this is only in one point of geodesic. What will be if we try to move along the geodesic? Is we can use the so-called Fermi coordinates. So we can parallel translate the set of normal vectors along the geodesic and then use this procedure. Okay, and so the procedure is the following: that even in Finsler geometry, we can construct something. We can construct Gaussian beams of both types, quasi-photon and quasi-jets, and corresponding all the items of this quasi-photon will have geometric sense. But of course, in Finsler geometry, it's rather complicated, because even such simple things as orthogonality or angle between two vectors, it's impossible to define correctly. What does it mean, the angle between the two vectors? It's impossible to define in Finsler geometry. So this is a much more complicated thing. It's necessary to be very careful when you deal with these things. Okay. This is if you try to construct this procedure for Finsler geometry, we obtain Riccati equation, but somewhat more different things. This is appeared additional tensor besides third Cartan-Kovachev tensor. So it is not absolutely trivial things here. If you try to use more complicated geometry, and if you try to construct, for example, for arbitrary anisotropic media, it will be even more complicated because even geometry doesn't exist very good on a good level. So we have to be rather careful. So I believe that I show that geometry is on the basis of any inverse problems. And in fact, if you plan to do something in the future, there may be three main directions of developing. The first one is try to compute, to make computation, to solve inverse problems using the good procedures, BC method or D-bar method or something like this. Just now it is only test model problem and test examples of this computation. I believe that no one method can compute something like I showed Asmarmuzi model in a good way just now. But it is for next generation. The second step for inverse problem is the problems with several geometries. It's a very complicated things. For example, if you take elasticity equations, standard elasticity equations, then corresponding inverse problem not solved in a good way, I should say. Because the problem is there are no corresponding Holmlund-John uniqueness theorem. We don't know what's the field by means of this wave. Here we know that if we start from this gamma and look for the time t, then wave fills this domain. So this is the set of waves dense in L2 here. But what will be if there are several waves? Of course, it can't fill completely this domain. And this is a big problem, analytical problem. It is for next time of scientists. And also there is another problems. Try to solve anisotropic problems. And if you try to solve an anisotropic problem, for example, such problems are the following: that if we have how to say, even can for beer, for example, let's take this one. This is produced by means of how to say, how this process, I don't know how to, it's English. Yes. And it's an anisotropic things in the result of this process. In fact, most of the complicated objects, the surface are specially improved. And this improvement produce anisotropic object, anisotropic material. And try to find out properties of this anisotropic material, anisotropic surface. You need to use anisotropic equations. And if you use the anisotropic elasticity or maybe different type, it doesn't matter. If you try to use anisotropic equations, you inevitably comes to the problem of Finsler geometry. Inevitably, you can't avoid this. So we have to, first of all, to find out the instrument which is suitable for this to describe these geometrical problems. One of these instruments, as I believe, is a quasi-Gaussian beam solution, different type, because it is suitable. It contains geometrical object in itself. And the second problem is that geometry are more complicated, so we have to be more thoroughly, more careful, because some of the how to say, the traditional solutions, traditional ideas maybe not work. This is what I want to say. Okay, I believe that this is what I want.
In order to apply this to a physical problem, like this problem in geophysics, so as far as I understand, people would have to test your physical system with these Gaussian beams or quasi photons.
First of all, we have to test what kind of geometry lies inside these physical problems. I believe that what type of geometry and quality of geometry or complicatedness of geometry is the most important things for solution. What I want to say. Yeah. And we can use the Gaussian beam to solve these problems.
Yes, but the Gaussian beam is an asymptotic expansion.
Yes, it's high frequency asymptotic solution.
So,
yes.
Would you somehow have to worry about the error of this, because I mean you have theorems like for this asymptotic expansion, and sometimes the errors may be not uniform in time controlled.
Sure. There are a lot of investigation. It's more than 30 years old stuff. So this is a lot of papers which are related to the computation of Gaussian beam, estimation of errors, and so on and so forth. For application, if of course it depends on how complicated the geometry, the same geometry. If geometry is how to say, the velocity change very rapidly, then errors increase. If rather small variation in geometry, then errors will be small. This is quality answer. But of course, it's for particular problem, it's necessary to make some investigation or use special previous investigation or something.
Could you just scroll back to the geophysics example that you mentioned, because I wasn't quite clear what was going on. Yeah. So,
this one.
You said that the color scale is the
color scale is for velocity. Velocity profile. That's if it's colder, then smaller.
That's the sound, the speed of propagation.
Speed, yes.
Yeah. And so you said you're looking for the internal boundaries. Where are the internal boundaries there? Are they the red things?
In fact, internal boundaries interested in this domain. You don't see them. These boundaries, of course, they exist. You see them, but it is not how to say. There are no oil.
But is that a
internal-
discontinuity in the sound speed? Is that what you mean by internal boundaries? What exactly is the internal
the
boundary?
oil deposit, I'm not, how to say, geophysicist, but oil deposit is somewhat in how to say, the hole
Yeah.
in the S crust.
Right.
And so there's big difference between the elastic media outside this and elastic properties of inside this where is the oil.
So it's a discontinuity in the sound speed that you count as an internal boundary. Is that right? It's because it's a discontinuous change there.
This
And
discontinuous.
the rest of the
Due to
change is
this,
smooth.
this is how to say, the liquid somewhere. The properties change dramatically
Yes.
in the boundary. You see, but if you actually look at the velocity, it is not so different. You don't how to say. You see that if you try to compute, so we see something like this. Are there any boundaries or not? But here, more or less, we see that there is some boundaries which maybe contain oil deposit.
And on this picture, that's the same. That's the
This is the model. This is the model. The same model, but in different scale, just
Yeah.
different scale.
And the white areas, are they internal boundaries on the second picture down?
This one,
Yeah. So are they internal boundaries? The white areas?
the internal boundary is somewhere here. We don't see them.
I
That's
see.
the problem.
Okay.
In fact, it is not very correct things. I believe it's not completely correct procedure. They believe that they know the velocity profile.
Mm.
But if you know the velocity profile completely, so we know the internal boundaries.
Yeah, exactly.
But they,
Right, that's-
so there is some kind of, but it is really real procedure. They really use this type of procedure. You see? It was a good idea to try to use the good mathematical method as BC method or D-bar method or something like this on such kind of model. Try to see what we can construct. Because in this case we don't need to know the velocity profile. We compute velocity profile. But the model is too complicated. This is the problem. This is the problem. Just now, as I said, we can compute it only on the tested model problems, not for this complicated. This is more or less real problem, I should say. It is not so kind of test, but test is very close to reality.